Assalamualaikum and a very good day. We are from Group 6 and our task is to produce 100 kilograms per hour of polyamide. The group members of Group 6 are Tom Zemfem, Satish Kumar, anak lelaki Palaniapan, Osama Muhammad Salibatis and Muhammad Hazim bin Harul Ishaq. Let's start with the introduction. So what are polyamides? Polyamides are also known as nylons. They are synthetic polymers. They contain repeating amide linkages or CONH. So what are they used for? They're often used for textiles, apparels, carpets and also packaging films. The two nylons that we'll be focusing will be nylon 6 and nylon 6,6. Nylon 6 has a monomer of caprolactam, while nylon 6,6 has a monomer of hexamethylene diamine. The reaction for nylon 6 is ring opening polymerization, while nylon 6 is condensation polymerization. The characteristics for nylon 6 is lower mechanical strength, stiffness, and has good flexibility. It has also good impact resistance. Whereas for nylon 6,6, the characteristics are high mechanical strength, stiffness, and melting point, excellent wear resistance, and chemical resistance. To begin, we will first look at the condensation polymerization, which is one of the most common routes used to produce polyamides. Condensation polymerization is widely used in the production of polyamides, such as nylon 6,6. In this process, a diamide reacts with a dicarboxylic acid, forming amide linkage, while releasing water as a byproduct. As the reaction proceeds, long polymer chains are formed through repeated condensation steps. This type of polymerization is typically equilibrium limited, meaning that the removal of water is essential to drive the reaction forward and achieve high molecular weight. As a result, condensation polymerization often requires high temperatures, extended reaction times, and additional separation steps to remove the byproduct water. Because of these requirements, the process can be more complex in terms of reactor design and operation. However, for nylon 6, it is used a different synthesis route. Nylon 6 is manufactured primarily through ring opening polymerization of E-caprolactam. In this process, E-caprolactam, which is a cyclic amide, undergoes ring opening initiated by a small amount of water or other activators. Once the ring opens, the monomers link together to form long polyamide chains. Compared to the condensation polymerization, this route is simpler as it involves only a single monomer and does not continuously generate water as a byproduct. This makes ring opening polymerization particularly suitable for continuous reactor systems, such as a plug flow reactor or cascade of stirred tanks. Due to these advantages, ring opening polymerization is the preferred industrial route for nylon 6 production. Hence, for this case, we will be choosing nylon 6 as our reaction. Next, we will discuss the typical operating conditions used in the production of nylon 6. Nylon 6 polymerization is carried out at elevated temperatures to promote efficient ring opening and polymer chain growth. Typical operating temperature ranges between 240 to 270 degrees Celsius. Operating within this range ensures high reaction rates while minimizing thermal degradation of the polymer. The process is usually conducted at pressures ranging from atmospheric pressure up to 20 bars. The use of elevated pressure helps prevent the evaporation of E-caprolactam at high temperatures and ensure that the reaction remains in the liquid phase. A small amount of water, typically between 0.5 and 3% weightage, is added as an initiator for the ring opening reaction. While water is necessary to start the polymerization, excessive amounts can reduce the final molecular weight of nylon 6 and must therefore be carefully controlled. Under these operating conditions, monomer conversion of 90 to 98% are commonly achievable. Residence times are typically several hours, especially in a plug flow reactor, which provides better control over molecular weight distribution and product consistency. Typically in the industry, there are two types of reactors used in this reaction. One of them would be the CSTR. It has good temperature control and uniform composition. However, it limits molecular weight due to the backmixing. Hence, this is where PFR steps in. The PFR allows a high conversion and better molecular weight control due to the minimum backmixing. Hence, in our project, we will be discussing on the PFR calculations.
Nylon 6 hydraulic polymerization involves multi-simultaneous and reversible reaction, not a single reaction pathway. It's a step-broad equilibrium control process, strong influence by temperature, water content, and residence time. Because its conversion, molecular weight, and byproduct involved together. Single reaction models are inadequate and a multi-reaction kinetic model is required for realistic reactor design. Okay, now reaction networking involves ring opening of collaborator, poly condensation between end group, and poly addition to growth chains. In addition, cyclic dimer reaction occur as a side reaction. Those cylindrical species are undesirable because they are reduced spinability and product quality. All 5 reactions are visible and occur simultaneously. All reactions are end group catalyzed, mainly by carbonic end groups. Reaction rates are exposed using forward and reverse term with an equilibrium constant. Rate constant follow the Hertzian equation, so the temperature directly controls both conversion and molecular weight growth. Again, the model assumed as a homogeneous isothermal melt with no mass transfer limitation. Pressure effect on electrostatic kinetic are negligible. Pressure involves only water monomer evaporation through the phase equilibrium. consistent with the Tai et al. Based on 1982 journal. Single reaction models fail to predict equilibrium effect, molecular weight, and cyclic diameter formation. Multi-reaction kinetic identify an optimal operation range of 260 to 270 Celsius. High resin time increase conversion, but molecular weight shows diminishing gain. Plug flow reactors favor higher molecular weight due to the minimal back mixing. Kinetic parameters were obtained from multiple journal sources, including Tai et al., Ramshasen and Nagasubramaniam, Raisin and Denner, and Agrawal et al. So, active energy typically ranges from 70 to 120 kJ per mole, valid between 240 and 280 Celsius. Frequency factors are taken from literature or fitted during the calibration. Those data are used for reaction modeling, simulation, and sensitivity analysis.
For the simulation, we use the advanced kinetic model defined by Tai 1982. Unlike the simple model, our script tracked 5 simultaneous reversible reactions, allowing us to predict not just polymer growth, but also the formation of side product impurity. We implemented this using MATLAB OTE45 solver to calculate the exact concentration at every second of the reaction. We performed 2 critical analyses. First, the kinetic profile on the left showed that the reaction reached equilibrium around 12 hours and achieving nearly 69% conversion. Second, we ran a stress test on the right. This simulates what happens if you rush the process. As you can see, pushing the flow rate too high causes a rapid drop in performance, confirming that our calculated residence time is critical for quality. Here is our final design specification. To straightly meet the target of 100 kg of nylon 6 per day, our simulation sized the reactor to exactly 76.6 liters. The reaction achieved a monomer conversion of 69.54% and a final yield of 99.74% with an extremely high selectivity ratio of 390, indicating the process is highly efficient at producing polymer rather than side product. To account for the equilibrium limitation, we calculate a required fit of 147.11 kg per day. Our mass balance verification confirmed that this input exactly matched the output.
So here's our reactor design, which is a BFR, called BFR, and there's assumptions made, which is the reactor an ideal behavior, and also the temperature constant along the reactor. And there is also the diameter and the number of turns of the coil that's already assumed. And also on the right side, the basis and the equations used in the calculations. So here's our reactor design, which is BFR. Here it shows that from the basis we can find and the diameter assumed, we can find the length of the reactor, and we can find the ratio of the L and D, which is 97.5, which is good. And after that, we can find the number of pitch from the equation of the coil, which is 140 millimeters. So here is the drawing and the labeling of our reactor design, which shows the labeling of our inlet and outlet streams of the feed, and also for the cooling or heating fluid if needed. Also showing from different views, up view, the top view, bottom, from the front side as well, and also showing the sectioning, also showing the diameters of the inlets. It's actually labeling and showing it correctly. That's it for my part. Thank you so much. So here is the drawing and the labeling of our reactor design.
To wrap up, we used the advanced kinetic model to design a reactor capable of meeting the 100 kg per day target. Our simulation proved that a 12-hour residence time at 260 degrees Celsius is optimal, giving us a nearly 69% conversion while maintaining the high selectivities against impurities. The final design resulted in a compact 76-liter column requiring roughly 147 kg of daily feed to balance the reaction equilibrium and hit our production goal.